Hello, welcome to the second demo of the project number 1 by Ricardo Castro and Emilio Holt for EE440. Today we'll be talking about the bifacial panel model. Previously we discussed the fixed tilt system, but right now we're looking at rows of bifacial. So these one don't move, they keep straight, and they're also compact into rows. So we created a script. It's gonna have these libraries, it's gonna have variables. We're also taking a slider with a 3D graph. It has a mathematical model that is on the project because we have taken a lot of time to make sure that we have a lot of scenarios covered. We also have created these objects, 3D objects with arrays for specifications that we want. So let's run this script. So if we compile, you're gonna create it's gonna give us in the command prompt, it's gonna guide us. So for example, for the day, assuming I want to do November 24th because that's my birthday, that would be day number 328. Latitude cruises 33 degrees north. Height of the beam, 5, doesn't have to be 2 meters, it can be more. Length of the solar panel, 2.1 meters. Row separation, 3.5 meters. Okay. After we create the executable, it's gonna create this space for us. It's gonna have tiles, it's gonna have the grid and everything that was very similar in that sense to the fixed tilt model. Now, something that I want to talk about briefly, on the other model we had west over here and east. I'm sorry, I already fixed that. The sun comes from the east, travels to the south, and then settles down on the west. When we're in the northern hemisphere, of course, if you're in the southern hemisphere, it will still rise from the east, travel north, and then settle west. Okay, so 2 a.m., of course, the sun is not yet up on this specific day. It will not get up until 7 a.m. We have a very small shadow. So at this point, we have a small shadow over here. So the sun is in the southeast, but it's very, very small, you can tell. So the scientist, for example, or client, can play around with this module. So for example, before noon, we have a sun around here in the southeast, and it will cast a shadow on the northwest. Now, just like in the other one, because we have very long rows across the x-axis facing south, we really care most about the y-axis distance relative to the beam for the shadow. So, for example, this 1.6 is the vertical distance between point A and the beam along the y-axis. Because if you think about it, there's going to be very long rows that's going to cast a shadow that's going to grow over here, and the scientists can make decisions on where to plant in this area. So they're more looking for the distance, the y-distance across the beam, not really about the x-axis, because we can assume that the rows are going to be long enough for them to plant. So for example, the client can make decisions about where to plant. It could be over here, depending on what season. So when they want to make informed decisions, they can take account of the distance in meters to high precision with all the information they really need. If they want another scenario, they can close, recompile, and rerun. Again, this works for northern, southern hemisphere, every day of the year, with all the specifications. So I hope this helped, and thank you.